Bismillahirrahmanirrahim. Welcome to this session on data structures and algorithms. Today's main topic is sorting. But before we build our intuition of sorting, we'll have to look at some building blocks. And using those building blocks, we'll design different sorting algorithms. And as part of this whole exercise, we'll also be doing some practice problems. So let's start with the building blocks. The first exercise is that given an arbitrary array of n integers, how will you find the farthest pair? Farthest pair means two integers with maximum possible difference between them. So I would strongly suggest that pause the video over here, focus on the problem, and try to figure out your idea. How will you find the farthest pair of two integers given an array of n integers, and those integers have been given in any order. So devise your idea and try to check correctness of your idea on a few examples that does that really work. So I hope you would have paused the video and figured out the idea. So by farthest pair, we mean the pair of two integers in a given pool of integers which have the maximum possible difference between them. So the smallest and the largest elements in the array are the elements which have maximum possible difference between them. So this is a rewording of the question that given an array, you have to find the smallest element, and then you have to find the largest element and just output both of the smallest as well as largest elements. So this will give us the farthest pair. So if you recall the idea of scanning an array. So for example, if we have been given an array of n integers, let's say we have an array of 5 integers. So they have been sorted in some order, and that order is not necessarily the one which is this one. This is just an example. So in order to locate the smallest element, what we need to do is that we need to scan the whole array. We need to start from the first point, and we need to scan the whole array. And when we reach over here, we should be having the answer that the smallest element is 1. And same way, we need to scan the array once more, or maybe within the same scan, we need to keep an additional variable to keep track of the largest element. And after scanning the whole element, we should be having the output 8 as the largest element. So 1 and 8 are the smallest and largest elements respectively. So if you find the difference, that is 7. So there are no two other elements which have mutual difference 7. So we have to find a pair which has the maximum possible difference between them. Now, in order to find the smallest and largest, what we are essentially doing is that we are scanning the whole array. In the scan, at each element, we are making a comparison. So one comparison takes big O 1 time, and in total, we are performing big O n comparisons. So one scan takes big O n time. So even if you do the scan twice, separately for smallest and largest elements, so you'll be doing big O n and big O n. So that will give us big O 2n. And in terms of big O, we'll still be landing onto the complexity of big O n in this whole problem. Okay, let's move to the next exercise. Given an arbitrary array of n integers, how will you find the closest pair? So the only change in this exercise is the farthest pair has been replaced with the closest pair. So we have to find the pair of two integers such that their difference is minimum possible across all other pairs. So pause the video over here, try to deliberate, think about the idea, how will you find it? So if you pause the video, you would have come across the idea, I hope, that this is not a similar problem as the one which we have just solved in exercise 1. So this problem cannot be solved without having the elements all in a sorted order. So we must have to have all elements in sorted order. in order to figure out the closest pair. So once the elements have, because why we need to have all elements in a sorted order? Because whoever is the closest pair, those elements must be just located next to each other in a sorted sequence. But if the input is an arbitrary sequence, the first task is going to be that we need to first sort those elements, and then we need to figure out that which pair is the farthest pair. So for example, if we have this sorted sequence, so then the pair which is the closest one is 14 and 16, because their mutual difference is 2. But if these elements would have been given in a shuffled order, in an arbitrary order, in an arbitrary order, then we'll have to sort them first. Now our task is that how easy or difficult is the sorting process. Okay, the first building block which we are going to have a look at this is called insert building block. So the input is an array of k numbers such that first k minus 1 numbers are already sorted in ascending order and the last number is out of place. For example, if you look at this example, so 1, 3, 7, 9, 13, and 23, all numbers given in black are pre-sorted. So this is the characteristic of the input. So input has been given in a sorted sequence such that first k minus 1 elements, which means that all elements other than the last one are sorted, but the last one is out of place. So our task of this whole procedure or block called insert is that we need to generate an array of k elements such that everyone is sorted. Every element in the array is sorted. So in that way, what we need to do is that we need to insert k into its appropriate position. So the kind of stuff which we are interested in doing over here is that if you look at the input, so 4 is the number which is out place, which can be out of place. So for example, if 4 would have been 400, then we'll just compare 4 with 23 and we'll decide that 400 is greater than 23. So we don't need to do it. We don't need to do anything in the array. We don't need to make any change. So after one comparison, we will decide that 400 is at its right place. Because if it is greater than 23, then it would be greater than all other numbers because all previous numbers are pre-sorted. So that is the best case. So in the best case, we might be ending up into something which is big O 1. But as 4 is given over here, so 4 is not greater than 23. What we need to do is that we need to shift 23 in place of 4, and 4 will go in place of 23. Then 4 will get compared with 23 with 13, and then we'll keep on comparing it with 9. It will get compared with 7, and then when we try to compare it with 3, that will be the place where we'll be like deciding that nothing is required. We have shifted every element toward one step towards right, and this space will be given to 4, and then 4 will get inserted over here, and as a result, this whole thing will give us the sorted output. But this is not a sorting algorithm. Why? Because it is based on a very strong assumption that first k minus 1 numbers are already sorted. And we are just inserting one new number into a pre-sorted sequence. So in the worst case, you might have already noticed that in the worst case, we might have to shift every element one step towards right. So in the worst case, the complexity over here is going to be big O n in terms of if n would have been the total number of elements. So big O n is going to be the complexity of one insert call. So if insert has been written as a method or function, so we'll have to perform big O n steps in the worst case to get an element which is out of place inserted at its right place. Okay, now the question is that, not really the question, but this is a like homework kind of exercise because we've already like walked through that what does this insert procedure mean. So just to make your concepts clear, you can pause the video over here and write the algorithm of this procedure in terms of pseudocode or maybe in terms of Java code. And then we have to figure out that how this algorithm can be used for sorting. So that is the most critical part of this whole exercise. So let's have a look at that. So for example, if we have been given 5 elements which are in some order. So let's say these elements have been given to us as an arbitrary input, and our task is to sort all of them. But the restriction is that we have to use this insert building block, which we would have designed by now, to uh, to be repeatedly called over here in a certain fashion, such that the overall input is sorted. So now, if you look at the characteristic of insert procedure once more, it expects that first k minus 1 elements are already sorted. And that is not the case over here. So what will be the safe k minus 1 value where we can decide that these k minus 1 numbers are already sorted? So if k is 2, k minus 1 is going to be 1. So we can safely say that this part of the array is pre-sorted because there is only one element. So this element in itself is sorted, and we don't need to make any comparison if we just focus on this green part. So 5 is already a pre-sorted array, and we only consider the next element, which is 3, to be inserted in the green pre-sorted array. So when we try to insert 3 into this pre-sorted array, 5 moves one step towards right, and 3 takes place of 5. And now after performing this one operation, what we have at hand is that uh, we have elements which are like now 3, 5, and they're pre-sorted. And sorry. So 3 and 5 are pre-sorted, and now this part of the array is pre-sorted, and we just need to take care of 9. So 9 is compared with 5, and it is greater than 5. So we don't need to make any further comparison, and we just bring 9 inside this group of pre-sorted numbers, and we decide that this part of the array is now sorted. So far we have made 2 insert calls. So then we consider 4, and we make another insert call. We try to insert 4. So 4 is compared with 9. So 9 comes here. 4 goes here. And then 4 is compared with 5. So 4 goes here, and 5 comes in place of 4 over here. And as a result, what we get is that this will be the kind of shape of the array. 5 would have in here. And now all these green elements are pre-sorted. So our array is sorted till this moment. And now we make the insert call once more. We try to insert 6 over here in the pre-sorted array. So 9 moves over here. 6 goes in place of 9. And then we try to compare 6 with 5, and 6 is greater than 5. So no further comparisons, and our insert procedure will stop. So we'll be having this shape of the contents of the array, and they are now sorted 3, 4, 5, 6, and 9. So we actually call insert procedure n-1 times. So what we know is that one insert procedure takes big O n time in the worst case. So if we are calling it n times or n-1 times, so this will lead us to big O of n square. So this is our first sorting algorithm which we have devised, which is using insert procedure again and again as its building block, and it takes big O n square. And this procedure is called, this whole algorithm is called insertion sort, because it's based on the insert procedure. So insert in itself, in its isolation, does not really sort the arbitrary array, but if it is called in a in a well thought and well organized manner, then it enables sorting. So this whole algorithm is called insertion sort. Okay, let's move forward. Let's have a look at another building block, which is called move min. And move min has the input that all elements given in the array are unsorted. And the output is that it outputs all original elements which were given to us, except that the smallest element is located and moved to the first position. So for example, if this input has been given to us, then the output would be that it will scan the whole array. It will find the smallest element. So in this example, the smallest element is 1. So 1 will be moved over here in place of 74, and 74 will go in place of 1. So all original data has to be preserved somehow, but the major change is that the smallest element has to go to the first position without losing any data. Now, if you just imagine a sorted sequence or sorted array, in a sorted sequence, the smallest element is always the first element. So if you just try to consider this move min as a building block of a sorted algorithm, then that means that if we call it once, it will at least be placing one element at its right place where it should have been if the array would have been sorted. Because the smallest element is the element which has to go to the first index. So that's what is happening over here. And now if we look over here, so this is one movement call. So if we ignore the first element, if we ignore the first index, and if we just look at these elements and we call movement once more, then the smallest element in this green box will be located and will be moved to its first index, which is now occupied by 23. So 4 is the smallest element that will take place of 23, and 23 will take place of 4. And another element has been placed to its right place where it should have been if the array would have been sorted. Now we keep on doing this whole exercise again and again until we reach at the last element, which does not need any comparison, and that would be at its right place. So movement can be called again and again to sort an array. So again, as part of your exercise or your homework, try to write this algorithm in a neat fashion, preferably in the form of Java code. And its complexity is big O, because we have just figured out in one of our previous problems that complexity of just finding the smallest element is big O. So move min finds the smallest element and then it swaps that element with the first index. So that swapping is just big O operation. So the total complexity is big O. And if we keep on calling it again and again, that will give us a big O times n. So big N time n will give us big O square. So this is again a big O square complexity algorithm, and this sorting algorithm which uses movement as its building block is called selection sort algorithm. So this whole strategy is selection sort. So remembering names of these algorithms are important because usually people ask you in the interviews that what will be the complexity of selection sort, or someone might be asking you to give you or present the details of selection sort. So let's move forward. So what we've seen is that we saw that we are using insert algorithm as a building block. We figured out its worst case complexity as well as best case complexity. And now your task is to find those examples for the best case and the worst case. Same is the case of selection sort. We have figured out the worst case and best case complexities, try to write them more formally, and try to come up with the exact examples which reflect the worst case as well as best case scenarios. Okay, now what kind of characteristics we are looking for in terms of a good sorting algorithm? So if there are duplicate numbers in the input, so for example, if there are two 5s in the input, so do we really need to differentiate them? The answer is that if they're just fives and they don't have any other meaning other than the visible numbers, then we might not be able to really, we might not really be interested in differentiating them. But if there are two names, like there are two alleles in our input data, and we are applying a sorting algorithm, so do we need to really differentiate them? And the answer is yes. So now there is a tie. So for example, if you're maintaining a queue, and there are two alleles, so like if there is a tie, both of them have the same key, so then we might be interested in processing the element first who came first in the input, and the element who was later in the input, we might be processing it in the later in the output. So that kind of characteristic, the algorithm which takes care of this characteristic, that the element which comes first in the input and has a tie with some other element, should be presented first in the output. Uh, and such algorithm is called stable algorithm. So once you would write the code for insertion sort and selection sort, I would strongly urge you to figure out that how you will be differentiating them. And this is just a matter of less than or less than equal to kind of thing. Okay. Another exercise is that are insertion sort and selection sort stable? So if we are writing a casual code, they might not be stable. And try to figure out the exact situations. I have already given you a hint a while ago that how to make sure that insertion sort and selection sort are stable. Okay, so stability is one characteristic of a sorting algorithm. Another characteristic is that does your algorithm demand a lot of additional memory space to run? And how much? If it expects like a couple of fixed number of variables, like temp variables, in addition to the stuff which you are using as part of your input memory, then we call it in place algorithm. But if your algorithm is expecting a lot of additional memory, which means that it might be copying your whole input into another temporary space, then that algorithm is not in place. So insertion sort and selection sort are in place because they don't expect you to create duplicates of the input array. And the sorting algorithm should be accurate, should be efficient, besides the characteristics of stability and in place. Okay. And like we have somewhat practice problems. So the first problem is that we have been given an array whose name is capital L, which is sorted. And we have been given another array whose name is capital R, and that is not sorted. Our task is that we need to put them together in an output array such that both of them are sorted. But such that the overall whole input is sorted, which means that we need to combine L and R such that that whole big sequence is sorted. And we can assume that they have almost same size. So take a pause over here and figure out that what kind of strategy will work and what will be the complexity of your strategy. So if you pause the video over here, you might have figured out that one thing which we can do is that because left part or L part is sorted, so what we can do is that we can pick elements from the R part one by one, and we just keep on calling insert, and we call insert n times, and all elements of the array R will be inserted into the array L one by one, and we'll be making n insert calls, and the overall complexity will be n square. So essentially we are using an insertion sort, and we are going to get this whole thing done. But probably we might not be able to optimize it further, even if half of the input is already sorted. So our complexity is somewhat getting closer to what we saw in terms of a completely arbitrary input. Okay, let's move to another problem. Part of the problem is same as the previous problem, that array L is sorted, but now array R is also sorted. And both of them have same size. So pause the video over here, figure out that how can we leverage this thing to sort the overall input. So I hope you would have paused the video over here. So now we can like come up with something which is more efficient than insertion sort. So for example, if we have some numbers, let's say we have 4 numbers over here, and they are 2, 4, 6, and 8. And we have 4 other numbers over here on the right. Let's say they are 3, 5, 7, and 9. So this part is the right part, this is the left part. So what we do is that we arrange 2 pointers at the start of both of the arrays. So we know start of left array, we know start of right array, we compare these 2 elements. So whoever is smaller, we put it here. So 2 is smaller, we put it over here, and we move our pointer in that array to the next element. Then we compare 3 and 4. Whoever is smaller, we put it here, and we move the pointer to the next element. So the other pointer remains at the previous place. Now 4 and 5 are compared. Smaller element comes here, and the pointer moves to the next element. And 5 and 6 are compared. 5 comes here, the smaller element comes here, and the pointer moves to the next element. 6 and 7 are compared. 6 comes here, and the pointer moves to the next element. 7 and 8 are compared, and pointer moves to the next element. So now 8 and 9 are compared. 8 comes here, and as 8 is the last element, we have exceeded the valid range of pointers. So all elements of right array are placed over here. Now, if you look over here, that what was the complexity which we have encountered over here in scanning the whole array and placing everything in the sorted sequence? We have scanned L array once, we have scanned R array once. Size of L is N, and same is the size of R. So in other words, we have actually spent big O N complexity on putting these together in a sorted sequence. But the important thing is that both of them were already sorted. So we leveraged this property of pre-sorted arrays, and we did this whole thing in big O N. Now, this algorithm is the critical algorithm. I would strongly suggest formally write it once you are free from the lecture. So this is called merge algorithm. So one merge building block is the building block which just merges 2 sorted sequences in big O N. Our next task is to use this building block to sort a completely unsorted array. So we've already seen that which one is more convenient. We have compared their complexities. Okay, so the algorithm is called merge sort. So what we do is that bottom contains the input sequence. So all the inputs have been given, the whole input has been given in an arbitrary way. So our inputs are like 5, 2, 4, 7, 1, 3, 2, and 6. Now, what we can assume is that our merge algorithm expects that our input is pre-sorted. So, and this is an arbitrary input. So what we do is that we break it down into pieces. The smallest part of the input, which we can conveniently imagine that this is pre-sorted, is an array of size 1. This is another array of size 1. We apply the merge procedure and we get this output in a sorted sequence. Then we call the merge procedure once more over here, and we get this sorted sequence. Same way we call the merge procedure on these 2 inputs, and we get this sorted sequence. We'll call it over here, and the last element, and we get this sorted sequence. Now, the critical thing is that what is the complexity, what is the amount of time which we have spent so far? So one merge procedure takes the complexity or takes the time which is proportional to size of the input. So if input is smaller, if input is small, then its complexity is going to be small. And at the bottom, the input is of size 1, so its complexity is big O 1. But how many times we are calling merge procedure? We called it 1, 2, 3, and 4 times. In other words, we have called it n over 2 times. right? So on this last step, we have called the merge procedure n over 2 times, but because the input was very small over here, so in fact, input was of the size n over n, which is 1. And this whole complexity in terms of big O is now going to be big O n. So on the bottom, we have spent big O n to get the 4 sequences given in blue on the second last row. So then we combine these two, the 2, 5, and 4, 7 sorted sequences. We call this merge procedure, and we generate this output. We do the same thing over here. We call the merge procedure once more. Now, if you look over here, we are generating the sorted sequences, but our number of calls are getting halved. So this time, our the overall complexity has the overall number of calls are reduced to half, further half. Previously, they were n over 2, now they're n over 4, but our complexity of each merge call is now doubled, right? So whatever it was previously, it is now doubled. So if you're dividing it over 2 over here, that 2 is getting multiplied over here as well, right? So the net impact over here is 0. So in other words, this whole procedure is taking big N time because our number of calls are getting halved, but our input sequences are doubled. And we keep on doing this. So on the top, we call it only once, and that generates this sorted sequence. So we've called big O n times once more. Now, one thing which we have established is that one row is taking big O n time. And another important thing which we need to establish over here is that how many times we have to do this whole thing. So we did it, if our input size was 8, we did 4 times over here. Then we did 2 times over here, then we did 1 time over here. So the total number of times we are doing this whole thing is somewhat very similar to what we saw in the complete binary tree. So we have to do this whole thing log n times. And each time we are like, each row is taking big O n times. So big O n times log n is the total complexity of this whole algorithm, which is called merge sort, which is using merge as its building block. Okay, let's move forward and please take on and take pauses as you feel like things are getting a little complex, and have a good grasp over the concepts before you move forward. Why do we need sorting? There are so many good, decent applications. One was, which we saw at the start of the course, that searching in a sorted array is very convenient. That's what we call binary search, and that is log n time search, versus searching in an unsorted array, which is called linear search, and that takes big O n time. We also figured out at the start of this lecture that finding a closest pair needs sorting. Finding duplicates in data can be done conveniently using sorting. We can, if the array is sorted, we can compute the frequency distribution. We can find the kth largest element in the data, and many more applications. So last topic of today's discussion is that we are going to leverage another data structure which we have recently studied, that's called heap. And using heap, we'll be building a sorting strategy which is called heap sort. So given a heap, how to locate the largest element? Take a pause, just as a part of recap, answer yourself first that how to locate the largest element. So if it's a max heap, the largest element is located on the root. So in big O1, we can locate it. How to locate the second largest element? The better idea is that if we delete somehow the largest element, and if you recall the heaps, we know that deletion operation takes log n time. So if we delete the largest element, that means the largest element is gone. We can store it somewhere separately, and we can build the heap. So once we have rebuilt the heap, then the second largest element of the original data is now the root, and we can locate and get rid of that element in log n time. how to locate the third largest element. Again, get rid of first and second largest elements, store them somewhere conveniently in an order, and then do the same thing, same delete procedure for the third largest element. If we keep on doing it for all elements one by one, we'll be performing n times log n operations. And only small step if we perform in addition to what we are doing in deletion is that if we keep on storing them separately, we'll be getting the whole data in a sorted sequence. But the question is that the given input might not be a heap. The given input might be an arbitrary array. So we can use those elements given in the input and we can build a heap. And we know that inserting one element in heap takes log n. And if we have to insert all elements one by one, then that takes n log n. So the strategy that given a heap, given an array, n elements in an array, insert them into an empty heap one by one, that will take n log n time. Because one insertion takes log n, so inserting n elements will take n log n, so the complexities of just building a heap is n log n. Once it's there, then start deleting elements one by one, as we saw at the start of the slide, and that will take another n log n to delete all elements from the heap. But with every deletion, we just need to store them in an output array, like this, that the largest element goes at the end, second largest goes at the second last position, and so on. So the total complexity over here is going to be big O n log n, and this heap will serve as a strong underlying data structure to help us sort elements quite efficiently in terms of, so our total complexity is going to be n log n, which is similar to merge sort, but this complexity is much better than insertion sort and selection sort. So if this is a heap, I would strongly suggest that take a pause and figure out that how things will be deleted from here in order to make them sorted. So the idea is that I can do first few steps for you, that if 16 gets deleted, so we have to get rid of 16. So 16 is stored somewhere here, and then we rebuild the heap. So the larger element, so if you are able to recall that how we used to delete an element from a heap. So our idea was that we used to swap this element with the last element, which is 1 over here. So 16 used to become the last element and 1 will become the top. We'll disconnect it virtually from here. By disconnection, we mean that it will remain in the array, but we won't consider it as part of the heap. And then we'll bubble 1 down. So 1 will come here, 14 will go on top because we are rebuilding the heap. And then 1 will come down, 8 will go on top, and then this will be taken over by 1 and by 4, and then 1 will come down. So then we'll do the same thing for 14. So now 14 is our next element. So 14 is swapped with 1. 14 comes here. We disconnect this part with the heap, and 1 comes here, and we do the same exercise over here. So 1 is compared with 8 and 10. So 10 goes up, 1 comes down, then 9 goes up, and 1 comes further down. So now if you look at the array, underlying array, which is representing a heap, so 16 and 14 have been separated. And they are located at the last and second last indexes. So keep on doing the same thing again and again. And if you do it n times, our entire sequence is sorted. So the same thing has been explained in detail on the coming slides. So this is just for you. So first few steps we have already done. Like we have seen steps till part C, and I would strongly suggest that do rest of the things on your own, and then you can compare your answers with this answer sheet. Okay, that's it. We're done with sorting. So assignment number 5, sorry for the delay on this. So task 1 is that please implement a heap in Java. And task 2 is that use the appropriate methods of heap to implement heap sort. So this is the complete assignment 5. And this is the last assignment of the course. Thank you very much.